Okay, so our next speaker is Amir Burshtein, and he's going to tell us something about single photon splitting in circuits from phase strips to integrability.
Okay, so hi. So first of all, thank you, and thank the organizers for this really nice opportunity. My name is Amir. I'm from the group of Moshe Goldstein from Tel Aviv. And I would like to talk about our two recent works in collaboration with the group of Vladimir from Maryland and now EPFL. And his postdoc, Ron Kuzmin, is going to be faculty in Wisconsin. And both of these works deal with single photon splitting, as observed in circuit QED in superconducting environment. And as I'll try to tell you, this is not just a really rare and cool effect, but it also hides a lot of physics behind it. It also is actually a technology we can use to learn about different kinds of phase transitions. So let's begin with the question that led us to these works, which is a fairly basic one. And that is whether we can observe inelastic scattering in a cavity QED system. So if we think about an atom in a cavity and we have an electron at ground state, then an incoming photon can excite this electron to some excited state. And when this electron will decay back, it will usually emit a single photon. Now this would correspond to elastic scattering. We have the same frequencies coming in and going out. And the question is, can we see inelastic scattering? So for example, can we see 3 outgoing photons? And the answer is that this is possible in principle, but highly unlikely. And the reason it is unlikely is because what determines the coupling strength between electrons and photons is the fine structure constant alpha. And because alpha is a small number, the probability to have multiple outgoing photons is very small. But this would be different if we can somehow control alpha and can get it to the order of unity. So how can we control alpha? How can we engineer a high alpha? One of the ways to do that is to recognize that, well, one of the ways to write the actual alpha is as the ratio between the vacuum impedance Z0 and the resistance quantum RQ. And this vacuum impedance is exactly related to the vacuum, to the cavity in our cavity QED system. And the idea is that if we can replace our cavity with some different medium that's a different impedance Z, then we could get a high effective alpha. And to do that, we can indeed replace this cavity with something else. We can replace it with a transmission line. And this is a photo of the device that we used. It was fabricated by the Emanuele group. And you can see this device here. So basically, you can see an antenna here on the left for spectroscopy. You can see a transmission line here in the middle. Here at the end, we also replace the atom with an artificial atom, which is a squid in this case. And below it, we have a sketch of the system. Now, to get a high impedance environment, this is a technical detail, we need to use not a regular transmission line, but rather a Josephson array. And the kinetic inductance of these Josephson junctions, which you can actually see here in this photo, these grains, is what leads to a high impedance. But this is a technical detail. For those of you who are not familiar with the concept, that's fine. You just know that this is a high impedance environment. Okay, so how can we measure things in this setup? So we have an antenna, so we can do spectroscopy. And we heard about this in the previous talk, but let me tell you about it in my context. So the way to measure photons in the system is basically to transmit power into the system from this antenna and then measure the output power. It goes out, and this is what you see in this figure here. So this shows the reflected magnitude that is measured at the output. And the incoming power is very small. This is less than 1 photon on average. And what we can see in the output power, we can see modes of the system. So at each dip here corresponds to a standing wave that is formed inside this medium. And so essentially, you can see the mode of the system. And if we zoom in on these modes, you can see that they actually have some width. And this width exactly corresponds to their lifetime, right, to their decay rate. So by measuring these kinds of graphs, we can tell the decay rates of our photons in the system. Now, of course, to have a finite lifetime, to have a significant lifetime or significant decay rate, a high impedance environment is not enough. We also need some nonlinearity to dissipate our photons. And to do that, we use our artificial atom, which is a squid. So a squid is comprised of 2 components. We have a tunable Josephson junction, and we have a capacitor. Now, we saw this Hamiltonian several times in this conference, but for the purpose of this talk, I would like you to think about it as a Hamiltonian of an atom in the sense that we have phi, the superconducting phase, can be thought of as a coordinate of the particle, and then q, which is the charge, can be thought of as the conjugate momentum. And so we have a kinetic term, we have a potential term, and this particle can move, this coordinate can move in this potential, it can move, it can tunnel, it can do all sorts of things, just like any other quantum potential. Now, you see that we have two energy scales here. We have the Josephson energy and charging energy, and the ratio between them is going to determine the kind of physics that we'll see. So we need to think about two extreme regimes. The first is the regime where EJ is much larger than EC, which will give us a transmon. And in that case, we have a very large potential, so the phase is going to be almost classical. It's going to be localized around the minima, whereas if EJ is smaller than EC, which will give us a Cooper pair box, then we'll have strong phase fluctuations. And each of these regimes is going to give us very different physics and very different decay mechanisms for our photons. So let's begin with the previous case, which was our first work. So if you consider a transmon, and indeed EJ is large and the phase is localized around one of the minima, then we can take this constant potential and approximate it to a quadratic order because we only see this region, essentially. But of course, if it were quadratic, we would not see dissipation. We need higher orders. So the leading suspect for dissipation would be, for example, the quartic term, this cosine. But it turns out that actually what leads to dissipation, and I will not go into the details of the calculation, but the leading mechanism for dissipation is actually phase slips, which are tunneling events of the phase going between minima of this potential. So essentially what happens is that a photon from the array triggers a phase slip, so the phase moves to another minimum, and in turn transmits more than one photon. It can transmit 3, 5, or any odd number. And we were able to calculate this cross-section of this interaction between array photons and phase slips using incident calculus. And the nice thing about working with experimentalists is that you can go to the lab and ask them to check your results. And fortunately, it worked. So this shows you the decay probability of single photons in our system as a function of frequency for several devices. And you can see we get a nice agreement. And the important thing about this plot is that the values we get here, this is the y-axis, is inelastic decay probabilities of single photons, and you can see that we get very high results here. So we have probabilities which approach unity, which leads to, points to a significant decay that takes place for single atoms in our system. All right, so that was a previous work, and I would like to talk now, I would like to focus on our recent work, our new work, in which we actually look at a Cooper pair box. And in that regime, so a Cooper pair box means that the potential is small, EJ is small compared to EC. And as I said in the beginning, this corresponds to a fluctuating phase. And therefore, there's no sense in talking about phase slips because we need to think about localized phase positions to talk about phase slips. So, okay, and I should mention that this is also a regime which was recently addressed in paper by the group of Nicolas Roch from Grenoble. And what you can do in terms of theory for that case, you can treat this cosine as a perturbation because EJ is small. And you can do perturbation theory, and what you'll get from perturbation theory is a decay rate which goes as a frequency power law, where the power depends on lowercase z, which is the normalized impedance of this transmission line. Okay, so this is what you get from perturbation theory, and again, we can compare with the experiment and see that we have a very nice agreement. But when we look at this result, there's something weird that appears here, and that is the decay rate actually diverges whenever the normalized impedance is below 1. So obviously it means that there is something wrong with the theory. Decay rate cannot diverge. And what is wrong is that what it turns out that this operator is actually relevant. This cosine is relevant at low frequencies when the impedance is smaller than 1. And therefore, there is some emergent energy scale below which perturbation theory does not work. And actually, this is a manifestation of a more general concept, which is a phase transition that was predicted by Schmidt and Gudaev almost 30 years ago, which deals with a system very much like the one we have here, where we have some periodic potential that is coupled to an ohmic bath. And this is exactly what we have. We have a periodic cosine potential, which is coupled to a transmission line. And what Schmidt will have predicted is that we will see some phase transition, which depends on the value of the normalized impedance. So this is a phase transition, quantum phase transition takes place at 0 frequency and temperature. And if the normalized impedance is below 1, then we are indeed in the case where the cosine is relevant. We have an RG scale and the phase is localized at low frequencies because the cosine is important at low frequencies. Whereas if the impedance is above 1, normalized impedance is above 1, this cosine is irrelevant, we do not have an RG scale, and the phase is diffusive. And if you think about it in the context of superconductors and Josephson junctions, we see that this is exactly a transition between a superconducting state where there is a well-defined localized superconducting phase as opposed to an insulating state where the phase is diffusive and the charge is localized. And as I said, this is an old story. This is a prediction from the 80s. But it turns out that this is, and there have been some attempts to observe this, but overall it's a difficult task because to observe this phase transition, we have to apply DC measurements and also stay at low temperatures. And DC measurements might interfere with the system, they might heat it up, and they might cause all sorts of problems. And in fact, the lack of clear-cut observation of this transition led to some recent papers, a recent paper from the Saclay group from 2 years ago, which claimed the transition does not exist. And this led to some responses and some other papers. And what I would like to tell you is that our approach of using single photons is actually a very cool way and a very useful way to probe this phase transition. So the idea is that here we have a system which is actually sensitive to single photons. And this will alleviate the problems that come with probing the system with DC measurements. So the idea is the following. So we can measure the system using single photons. Unfortunately, the experiment does not allow us to probe all the way down to 0 frequency because there is some range in which we can probe the system, which does not go below the RG scale. But looking above the RG scale is still enough to see what's going on in the low frequency limit. So if we think about the decay rate I just told you about, then now we can understand this decay rate is actually a signature of the transition. So what do I mean by that? We see this decay rate. This is a power law which either diverges or converges depending on the value of z, lowercase z. And you can see this is exactly a manifestation of this phase transition because if the impedance is below 1, then this decay rate actually trends towards divergence, which indicates that there is some RG scale. Whereas if the impedance is above 1, then it means that the decay rate converges towards 0, which indicates the lack of an RG scale. So by looking at even intermediate frequency range, we can still learn about this transition and see this as a signature of its phase transition. But we can actually look not only at decay rates, we can also look at elastic mode shifts. So what do I mean by that? So the idea is the following. If we think about our superconducting phase, right, when the phase is localized and we can approximate at low frequency, approximate this cosine as a quadratic potential, then at low frequencies, this will look like an inductor, right? So this will be for the superconducting case, whereas for the insulating case, we basically eliminate this cosine potential from the picture because it is irrelevant to low frequencies, and we are left with the capacitor, which comes from here. And these are two linear elements. They will not cause dissipation, but they will cause phase shift. And this phase shift will behave differently depending on whether we are in the superconducting state or in the insulating state. So what we can do, we can measure mode shifts. And again, this is mode shift at intermediate frequencies, not low frequencies. But we can still learn about this transition from these measurements. So this shows this spectroscopy for one of the modes of the system. So we can see the mode, one of the modes here depicted by this dark blue line. And what happens in this figure is that we turn on the impurity. Remember, this is a squid, so we can control this EJ. We can turn it on and off. And so turning it on is going from either the top or the bottom towards the center. Right? This is where the impurity is on. And you can see that when we turn this impurity on, the mode shifts either to the right or to the left, depending on whether the impedance is below or above the resistance quantum. And this is, again, can be thought of as a signature of the transition, even though this is in frequencies above the RG scale. So the upshot of these last two slides is that we have a method here to probe the state of a system in a very gentle way without interfering with it because we use single photons. So this is a work that we're wrapping up right now, and hopefully will be out this month, I believe. Right, so, but how much time do I have?
You have 2 minutes.
2 minutes, good. Okay, so in the 2 minutes I have, I'd like to tell you a little bit about what we can do in terms of theory, also below the RG scale. So, or essentially at low frequencies. So if the impedance is above 1, we don't have any problem because we don't have an RG scale, so perturbation theory just works all the way. Right, but if the impedance is below 1, then we need something fancier than perturbation theory. And we can actually solve the system in the case where EC goes to infinity, which is the case where we eliminate the capacitor from this picture. And in this limit, and we should actually be more careful with that, there is some scaling limit that has to be taken. But in the appropriate limit, what we are left with is the boundary Saigono model, which was Lagrangian represented here. And this is essentially the same system that we had, but without the capacitor. And it turns out this model can actually be solved exactly. So a few words on how we can do that. So let's begin with the simplest case, which is the Z equals half case. And this is a special case when we can actually, what we can do, we can take this Lagrangian of bosons and introduce a fermionic field, which is proportional to the exponent of the bosonic field, as indicated here. And so what happens is that this part, this transmission line part, was quadratic and stays quadratic also in terms of the fermions, but this cosine actually becomes linear because this fermionic field depends on the exponent of the bosonic field. So if it is a quadratic model, it means we can solve it exactly. So we can obtain an exact expression. We can solve the system exactly in terms of the fermions and then introduce and then translate the results to the basis of the photons or the bosons. So what we can obtain is an expression for the reflection coefficient of the photons, and this reflection coefficient exactly gives us the decay rate and also the mode shifts of these photons. And we have some closed exact expression, which we can now compare with perturbation theory, and we see that we get what we expect to get an agreement at high frequencies, and we need the exact solution to understand what's going on at low frequencies. So this shows you the decay rate. And again, this is for the special Z equals half case. Now, the striking point about this calculation is that we are able to obtain properties of inelastic scattering in terms of the photons, even though the system is purely elastic on the basis of the fermions. Right? So we have a system which is quadratic on the basis of the fermions, which is obviously there is no dissipation there. But we still were able to calculate inelastic properties using this purely elastic system. And this can actually be generalized, and this I will just flash the results. This can actually be generalized to the general Z below 1 case, where we can use the fact that the boundary Saigono model is integrable. And then what it means is that we can actually, in the spirit of the previous calculation, we can use the fact that we can implicitly map our bosons to a system of free quasi-particles, which are neither fermions or bosons, or something else, but they still give us a framework for an exact calculation. And this is a more involved calculation, which essentially gives us an extension to the result I just showed you in the previous slide for basically any value of the impedance below 1 that we will want, where the power law is reproduced at high frequencies, and we need the exact solution to understand what's going on at low frequencies. So this is another work that hopefully will be done soon. So with that, I'll finish. So I just want to tell you that single photon splitting is possible in a circuit QED environment and hides a lot of physics behind it, how it can actually be used as technology to probe a phase transition, and there is some very interesting integrability stuff that we can do also with this model. So thank you, and I'll be happy for questions.